So I'll catch up here, uh, talking about how we use all that technology that makes world running, building Servercore Cloud. Um, it's interesting that in a cloud we kind of mimic lots of different approaches that are being used on a lower level at a data center level. So we have redundancy everywhere. We have lots of equipment that can catch up if something terrible happens. And we basically are just pulling up all that networking and uh, resiliency to the user level. So in the next part, we'll talk about briefly about Undercloud networks that was covered previously. And we'll see how they're connected with user level networks. With objects, you as a customer, as a user of a cloud can utilize building your applications. So in a cloud, we split many things into two groups. Things that are not visible for our customers and things they are interacting with. So everything we have mentioned previously in context of networking was so-called under-cloud networks. Under-cloud means that there is no way for a user to get an address from any of those networks. Here on these slides, on this slide, there are two networks, like net network, perfect naming, and SAN network. These two types of networks are provider level networks. They are high through output, offer lots of gigabits per second, and we use them to kind of host user level networks. So they are being fed one into another. And in today's talk, we'll exclusively focus on net network, SAN network for storage systems. They are a bit out of scope for today's talk. So now we are gonna zoom into this net network and see what it consists of. Typically, it consists of multiple layers. Only in some simple cases, like providers that offer VDS level style services, like single virtual machines with only one public IP address, they have simpler setup, like just a couple of routers and you're good to go. When you're building a cloud, offering your customers network drives, load balancers, and all that stuff, you just cannot afford using a simple approach. So you have to split your infrastructure into different layers, and we have done that. The top level consists of network equipment mainly. I will talk here about Servercore Cloud specifically, but the architecture is kind of standard. So you will find the same approach in many private clouds, in public clouds, depending on the size, of course. And the main part here is access router. Access router is something that makes public connectivity happen. So these are routers which can tell the world about public networks they are ready to accept. BGP, all that stuff happens here. Another part is Servercore feature. It's global router. At the same level, there can be like DDoS protection and other things that are to connect cloud with something external to this cloud. So access routers connect internals with internet, so with consumers. Global router, in case of Servercore, connect cloud with bare metal equipment you can rent in the cloud, or with your colocation equipment you brought to iColo, or to your office on-prem something. That's it. So equipment on this level knows about IP addresses and about routes, and they take care about it. On a lower level, we focus on distributing the traffic we receive from the upper layer. So we just use spine switches and leaf switches. So on this level, you typically won't find routers. They will be more simple equipment. We call them switches. They are to distribute traffic inside the pool between different nodes, between different objects like virtual machines and stuff. So if you are distributing public traffic, you will probably use network nodes for that as well. I will talk about it a bit later. If it's like traffic which is internal, which come through a global router, you will probably put them directly to compute nodes here. At this level, networking is optimized for horizontal traffic mainly, because when you process lots of data, you need everything run fast without going outside. So now we will focus again. So look, we are create focus and focus and focus. Now we will focus on this internet traffic, which is being processed by access routers. So we zoom in and zoom out at the same time. So we won't look at network equipment today anymore. So we will focus on network traffic and two main ways you will encounter studying the topic on the internet, testing different service providers. There are two ways to process public traffic. To use something in the middle, like network nodes in case of Servercore. It can be specific server equipment, network equipment. The main idea is that you are not passing public traffic directly to a virtual machine, Kubernetes cluster or something. You have a step in the middle to filter. I will talk about it later. Another approach, which is more typical for private clouds, is to connect a cloud entity directly to the internet. Just, yeah, with no points in the middle. So approach number one is something you will use, not probably noticing that, when you order one IP address from any cloud provider. So when you launch a virtual machine, say, yeah, it should be connected, you will have an IP address that will typically be provided you using this approach. The second approach is more typical for like I don't know, for instance, clouds built with VMware technology. They love this simplicity. Private OpenStack clouds on OpenStack also uses as well. So we'll start talking from about the first approach. What those network nodes are. Well, depending on the cloud, I will again here talk for Servercore mainly, but the information is available. You can read about this piece of equipment from public nodes of IBM Cloud, Google Cloud. At Servercore, we use just specifically built server equipment, just servers with CPUs, RAM, volumes, with network cards of this size, which are able to process like 40, 80 gigabits of traffic. And we have multiple nodes of this type per pool. Why do we have multiple nodes? Akinas has covered that. We cannot afford finding a new node if it fails. Thankfully, they do not fail every day, but we encounter one or two failures of equipment of this level per year. So it's always it's always good to be able to get everything running like in minutes, not spending multiple days building this equipment. Yeah. So let's see how this network node looks like when you are a customer. A network node is a place where we virtualize networking. So when you create a public IP address, no, let's start saying that the core object here on this level is a virtual router. It is pictured here in the middle. Virtual router is basically a programmatic approach to mimic behavior of a physical router. And in our cloud, we use OpenStack Neutron for virtualizing this networking function. And this virtualization allows you as a customer to create those routers, connect them to the internet, add to this router multiple public IP addresses, 1 to 100. You can set firewall rules at the same router, and also you can use like you can connect your servers to the internet without assigning a public IP address for them using NAT technology. In the future, when we'll finish working on this feature, VPN will also be available here to privately connect to a cloud project from the outside. And the next steps, I will show you how it's possible to create an infrastructure in the cloud using Terraform. Because this approach will allow me to picture details needed to understand why cloud networking is agile and fast and easy to use. By the way, do we have Terraform users here? Please raise your hand if you have ever used Terraform. Okay, I will like use a couple of minutes of your time to briefly describe what Terraform is. Terraform is a tool which allows you to write code like in a YAML file that it will process to create infrastructure in the cloud for you. So instead of clicking buttons or issuing CLI commands, you just write text. You write text, and after that, immediately you are able to apply it. If you made a mistake, you can destroy everything and reapply one more time, and you could repeat it until you have a desired result. What's also good with Terraform, you can share this text with your colleagues. You can use Git repositories, you can commit the changes for your colleagues to understand what have been done, why, what to do next, and so it's a good practice for teamwork. So in next examples, I will show how it's possible to use Terraform to create a project at Servercore Cloud and create objects inside it. What you start from is basically setting like playground for you. Like so, you define providers for Terraform you will use. At Servercore, we have to use two providers. We have our custom API, which allows users to work with roles, project management, some custom resources, and for this case, you use Terraform, Servercore Terraform provider, which is here on the first section. The rest of automation is done through OpenStack compatible API. We kept to ease migration to Servercore from OpenStack on-premise private clouds. So the rest of provisioning you are doing through OpenStack provider for Servercore. After you put required providers at the beginning of your Terraform manifest, you just give it like credentials. Terraform will use those credentials to go to the cloud and do actions you require in the text. The main name here is my account inside the Servercore cloud. This authentication URL is static. You can copy and paste it, use it in any of your automation routines. So what we start with is we will create a private network in a cloud. Inside this network like it's a level 2 object in networking field. It's it has nothing to do with IP addresses, but it's like a basis for any connectivity. So you always start with creating a network, and after that you create a subnet. Subnet is an entity that provides you with IP addresses. After you have created that, you will be able to see these objects inside a control panel. So you add this text, you issue command Terraform apply, and after that you see this in a control panel without clicking a single button. Networks are not those objects you will probably see anywhere, I mean, in a cloud infrastructure. It's just records in a database. Records in the database that at the same time allows your traffic to be split between different subnets, filtered, and very powerful. After we have created a network and subnet, we will create a router. Router is something we need to connect this infrastructure we have created with internet. So we start with creating a router and connecting it to a subnet we have just created. Again, router is a thing that is visible through the control panel. So after applying this configuration, you can go and check that everything works as expected. But at the same time, router is the first thing that you will be able to see inside a cloud infrastructure. As you remember, router is a central part of the network node. So each time you create a router, a new instance of virtual router is being launched on one network node. We have multiple, but on one of them you will spot it. And if you had an access to cloud infrastructure, you would be able to find this router on a node. So you just issue command ipnetns list. You grab with IP with an ID of the router from the control panel, and you see it. So it's not physical router; it's virtual, but you can actually almost touch it, interact with it. And if you dive even deeper, if you go to this namespace, you will be able to see this IP address, which you have seen in the control panel. Crazy stuff, but is easily controllable through an API. So let's get back to our initial plan. We create network and router. We create an external IP and set up a firewall rules. And on each step, we will see artifacts that are available from cloud infrastructure perspective, from control panel perspective. So the next part, after we have created a router, is to create a public IP for this router. As I've mentioned, we provision all this infrastructure through an OpenStack compatible API. In OpenStack, public IP addresses are called floating IP addresses because of their main quality. The main quality is an ability to reassign those external IP addresses between private addresses. Reassign very quickly with no interaction with a server. So we create a floating IP and assign it to a port of an instance. And when we do that and get back to this network namespace on a gateway node, we will find this public IP address added here. The whole operation takes around like 3 seconds. You issue a request to the API, and after 3 seconds you are good to go. The traffic flies. Let's take a look at what's also possible to do through this network automation stuff we have. We can set up firewall rules. Firewall at Servercore Cloud is something that lies below the router. So traffic can freely fly to the router through a public IP address, but when it's about to get out of it, trying to reach some part of infrastructure, it will get filtered. Let's say we want to create a firewall policy consisting of two rules. The first one will allow ICMP traffic, just for us to be able to ping our instances. Another one will allow a TCP traffic on port number 22. That's for SSH. We combine these two rules inside a policy and apply this policy to a router port we have created previously. And after that, if we go back to network namespace on a gateway node, we will also see these rules set up here. And this operation takes even less time. It's like sub-second, like something. This responsiveness of operations through an API enables us to build different scenarios, like high availability scenarios. For instance, when you use Kubernetes to launch something in a cloud, Kubernetes knowing how these IP addresses work will utilize that. For instance, if you have an application running in a node, in a pod on some node, and this node fails, Kubernetes will quickly launch a new node in a cloud, will migrate pod with applications or launch a new pod on this node, and will reassign a floating IP, so-called floating IP, public IP, with that node. And it relies on this responsiveness, this quickness that we provide to migrate load between nodes. And firewall rules provisioning is also need to be fast, because sometimes we need to react fast. It's very good that these operations takes not that much time. At the very beginning, I've mentioned that there are two main types of organizing public connectivity. And by now we have talked about the first one, which involves the usage of network nodes. There is another approach to avoid using those network nodes, using networks which are directly connected to virtual machines. Why it can be interesting? First of all, if you got used to using bare metal networks, because you have experience working with server equipment, you have your own servers, you got used to see an IP address directly inside like network configuration of your server. Directly connected networks are for you. So another positive feature here is that you have a full range of public IP addresses. And the first scenario, when you order IP addresses one by one, you will have them random from different subnets, sometimes completely different. And in case for some reason you lose an access to this IP address, you probably won't be able to get it back, because API will issue a new IP address every time you ask it for. But there are situations when you cannot afford that. When you really need to have your addresses in one block. For example, when you're building a product for some enterprise, like for the bank, they have firewalls on their side, and they need to understand. They need to know, like at the very beginning, from which IP addresses you will come to their facilities, and they will ask you, look guys, tell us the subnet you wish to come from. We will add this subnet to the firewall and we'll be good to go. If you have such requirements, public networks like public IP ranges for you. And at Servercore Cloud case, we also provide IPv6 connectivity inside this. Networks, they are not, it's not available directly through a control panel, but you can order it. It's free of charge, but you can ask cloud engineers to give you an IPv6 address range to use it. As direct connected networks do not use network nodes and virtualization layer here, typically network latencies will be slightly lower. Not much, like 2% is like the very top, but it can be important for you depending on the application and requirements. These networks are less flexible. You won't be able to quickly reassign an IP address from this network between different servers because this address should be set up on a server network interface. And in order to do that, you will have to use some kind of automation. Ansible, Puppet, any provisioning tool you need to use. And for now, this way of connectivity does not provide you with firewall or port forwarding technologies available when you use Cloud Router. So if you are using public networks, these IP ranges, you will have to set up firewall on each server which is connected to the internet inside the server. So that's basically it for today. To wrap up, we have shown that solid IT systems, when you launch something for your customers, need a solid base. You need to understand what will happen if something fails. If you bring your equipment to a co-location facility, think about how it will be connected, how much providers you need, how many providers you need here, what we'll do with I don't know, electricity on a server level, and things like that. Typically, redundant systems provide you with less headaches. So when everything is made with like keeping that things break in mind, you just come back online quickly. And automation. Cloud is really good with automation. Without it, it's just less interesting. So give Terraform a try if you haven't yet. Use this QR code if you like to get Terraform manifest. I've been showing today. It's really easy to use. Thank you for your attention. We have now time for questions, right?